So our first unit is on limits. And what a limit is something that you can get really close to. Sometimes you can even get to that value. So, for example, the difference is if I had a function, just a straight line, you know that when x is 1, y would be 3. And in calculus, we would say the difference between a limit and an actual value is a limit is saying, what happens when you get close to 1? Well, when you get close to 1, in this situation, it's pretty obvious that your answer would get close to 3. And so we would say that the limit as x gets close to 1 gets close to 3. And in a lot of cases, the limit is exactly the same as the point. Like if you can calculate the point on a graph, that's probably the limit on the graph, looking at what it gets close to. But we also have some situations where you get close to something but never get there. So for example, right now, I am about 16 squares away from the wall. And if I walk half the distance, I would walk 8 squares, and I'd still be 8 squares away from the wall. And if I walk half the distance again, now I'm 4 squares forward and 4 away from the wall. And then I could walk half, now I'm 2, and half, and 1, and half, and half away, and half of that, and half of that. And I could do that forever. Probably get bored, but I could. I could just keep cutting in half over and over and over again. Would I ever get to the wall? Would I ever pass the wall? No. But we would say that the limit, as I do this to infinity, would be getting to the wall. And you've done this because what I just described was grade 11 math. In grade 11 math, this is what I walked. I walked that forever. Imagining starting at 16 away, cut it in half, cut it in half. I would walk 8 plus 4 plus 2 plus 1. And if I did this forever, this is a geometric sequence. Do you remember this formula? For an infinite geometric sequence. And if I plug the numbers into that formula, my term 1, I walked 8 to begin with. I'm cutting it in half each time, so my R value is a half. If I evaluate that, that infinite limit says, if you do that for infinity, you will walk 16 squares. And it's really easy to imagine that because already, right, when I'm at a half and then a quarter and then an eighth and then and I keep on going for a long time, you're like, okay, Mr. Jarrett, we see you're basically at the wall, right? I say, come back and check in 5 hours. You come back and I'm like, okay, it's probably good enough. But eventually you'll be so close to 16 that we would say the limit as we go to infinity would be 16. But in reality, I never get there. At any moment that you say, okay, you can stop now, 5 years later. Oh, I'm so close, but I'm not at the wall yet. Taking out a tiny little ruler, measuring how far I have to move forward, and then moving forward. This is the idea of a limit, because there are going to be some places where that value in reality doesn't exist, but the limit exists. And in other cases, like this straight line, if x is getting close to 3, can you see that the answer is getting close to 7? Sometimes you're able to just plug in a value and find a limit. But other times, you won't be able to plug in a value to find a limit. For example, we are going to have questions that look like this. And I'm going to say, what happens when you get close to -1? And this is a problem. Because if I get close to -1, the number on the bottom is 0. And if you try to evaluate that, that's not possible. And so sometimes dividing by 0, weird things happen. And we'll have to try to figure out what is, if I get close to -1, does this actually get close to something? So what we could do is we could go to our calculator and type in -0.99999 and push enter and see what number comes up. And if it comes up to a number, we'd be like, oh, maybe it gets close to 0. Or if it doesn't come up with a number, then we might say, oh, maybe there is no limit on this value. So that's what a limit kind of is, and that's what our first unit is. After our first unit of limits, we're going to branch off into the two main types of calculus, integral calculus and differential calculus. As students, you will always learn differential calculus first. However, mathematically, integral calculus was done 1,700 years before differential calculus. Just kind of, it's weird in math how some things that are connected, they didn't know they were connected when they started working. Like, you know that exponents and logarithms are inverses of each other. So you would think they would kind of learn simultaneously, but no. Logarithms were invented for a totally different reason, and only afterwards they're like, oh, this is just exponents. So weird things like that happen. Here is some history. Integral calculus was used by the Greeks. And one of the most famous mathematicians of all time is the Greek mathematician Archimedes. He called his integral calculus the method of exhaustion. Doesn't that sound like you just can't wait to get into integrals? No, it's not that tiring. But his integral calculus is dealing with areas under curves. So, for example, you know how to find the area of a square or a rectangle. You've got length times width. You've got a formula. But if all of a sudden I take a parabola and say, what's this area under that parabola? You're like, ooh, that curve is kind of awkward. So what Archimedes did with his method of exhaustion is he said, well, if we split this into 4 rectangles like this, that's a pretty good estimate, but not perfect. What would make it a better estimate is if I maybe made 8 rectangles, because then I could do them in blue. I can make them, oh yeah, look at that. Those. Now, if I figured out the area of those 8 rectangles, that would be closer. And he's like, oh, you want to get closer? What would be closer than 8 rectangles? Right? Yeah, 16. And maybe 1,000. And maybe, oh, let's do, if I did 8,000 rectangles, tiny, 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 you'd probably be very, very, very close. So close that you'd probably feel like, that's good. So that was Archimedes saying, if we want to find area under awkward shapes, we can just do a bunch of little rectangles over and over again. Little did he know this is like integration and integral calculus. Exactly. And integration is connected to derivatives, but derivatives weren't really developed until the 17th century. And here's a fascinating part about math history, okay? So generally you'll see in textbooks now, it was discovered by Newton and Leibniz. So that makes you think, oh, were they working together? Absolutely not. Did they find it at the same time? About 17 years apart. Which kind of makes you feel like, so shouldn't one of them be the one who discovered it and the other one like copied it? But you have to realize that in the 17th century, it's not like the internet now, right? If you discover something new and you post it on the internet first, you can definitely say date stamp, I found it, somebody else copied. But in this case, they're saying that both Newton and Leibniz discovered it on their own without knowledge of each other finding it out, even though there was years in between. And they both have different aspects of notation that is really helpful. So there's good things from both of them that we still use today. But 100 years ago, if you had an English textbook, it would definitely say that Newton discovered calculus. And if you had a German textbook, then they would say that Leibniz discovered calculus. So they've also got this historical kind of fight between cultures and wanting to take pride in what they discovered. And science in those days was not like science now. Maybe science is still a little bit like this now, where people don't share things because they want to make money. But in those days, they didn't like to share information, and if you didn't like someone, like Newton was the, what's the name of that? There was a Royal Society for Scientists. I forget the official name of it right now. And he was president of it right after another scientist named Hooke. And Newton did not like Hooke. He destroyed every piece of scientific information he could get his hands on that Hooke had made. Destroyed his, we have hardly any pictures. He also destroyed pictures. It's like, wow. It's like, not nice. Scientists, you know, you think of your science, oh, they're all nice people, right? No, scientists are. No, just, all right, here we go. So, getting ready for limits. What is the stuff that you have learned in the past that you're going to need again? And sometimes I'd like to have my grade 12 students go to my grade 10 classes and say, do you know how important factoring is going to be? Like, have you had a year of math where you haven't had to factor? Factoring comes back over and over and over again. And again, we're going to be factoring for helping us figure out limits. And factoring, all factoring is doing is taking an expression that's adding and changing it to multiplying. And it doesn't seem crazy, but the first time that you really saw I think, the beauty of factoring, let's just pick one here. Quadratic equation like this. And right now, we can't solve this easily because it's adding. Three things are added together to equal 0. There could be so many possibilities. If you start trying, is it 1? No, it doesn't work. Is it? You might realize, okay, should I try -1? It doesn't work. We have a problem. Because you have guessing and checking could take a long time. What factoring does is it changes adding and subtracting to multiplying. And as soon as you change it to multiplying, if I tell you two numbers that multiply to equal 0, mathematically, you know what one of those numbers has to be. There's no way to multiply two numbers and get 0 unless one of them is 0. Try it with any of them. 2 times 3, no, that's not 0. 5 times 2, if you forget the 1, maybe. But no, unless you make a mistake, multiplying to get 0, one of them has to be 0. So this is the powerful thing. It says, oh, if this one's 0, then x is -4. If this one's 0, then x is -2. That's the whole reason that factoring was so powerful for quadratics. Sometimes you get so good at factoring, you just do this, that you forget to take a step back and say, why do we do this? And where does it come from? And it makes so much sense. Because the only way you can multiply to get 0 is if one of them is 0. And that's why in quadratic equations, you can never like, oh, I'm going to factor and keep this side to 5. Because if this side is 5, oh great, I have two things that multiply to 5. Could be 5 and 1, right? Could be something totally different, like 5/3 times 3. There's so many. There's an infinite amount of answers if it's equal to 5. But if it's equal to 0, then we have power. So factoring, which is super important, is going to be used a fair bit in limits. So we are going to revisit some of our factoring skills and extend some of our factoring skills to things that maybe you haven't done before. So try these on your own. I'll put up the answers in a second. So common factor, you're looking at all the expressions and seeing are there numbers or variables in common. In the first one, there's an h in common. If I take out that h, now I'm left with 3h squared plus 7h minus 1. And then you'd have to look at that and decipher whether you could factor that or not. So one of the things that factors requires, I feel, is you have to be able to do a bunch of mental math in your head fairly quickly. Because for this one, I would imagine trying to factor it by saying 3h and h, 1 and 1, and then checking, will that ever make 7 in the middle? And it won't. So I quickly would have to say, all right, this is done. I don't have to factor anything further. You have some other tools available to you. You have the quadratic formula that you could use to check if you could factor this, but this one, that's all you could do. For the second one, in the numbers, the 2, 8, and the 6, there's a 2 in common, and we have p's and q's in common, so you could take out a 2pq. When a factor completely gets taken out of like that first term, you've taken the whole 2pq out, you're left with a 1. Again, every time you factor, in your mind, you should quickly multiply it out again to check. Yes, that takes a little bit of time. But I will tell you that if you make one mistake factoring in a question, the amount of time it will take you to fix that mistake is like, where did I make a mistake? And now you're working over and over and over again. But if you take the time to do quick checks every time you do a step, you're going to increase your mental math skills and make less mistakes, which causes less frustration. Well, example 1 is one of my favorites. Why? I like that one. Because some of you are going to get it wrong. I'm not its favorite because you get it wrong. But you might get it wrong at first. Check. Make sure you check. Did you think of 6 and 4 first? And then if you checked it, it didn't work. Yeah, that's why I like this one, because 12 and 2 and 6 and 4 both make 10. And so there are a couple factoring ones out there that are kind of sneaky, because you might feel like, oh, I found it 6 and 4. But when you actually multiply it out to check, either you don't get positive 10 or you don't get negative 24. Something goes wrong. So it's a good example to look at where the mental math, it's very easy to see a wrong answer. And if you're not checking it, you'll just keep going and then perhaps have problems there afterwards. Okay? So 10 and 24 is one of those. Here's another one. Right? Because you probably want to do 2 and 3, but it's 6 and 1. Right? So I tend to point those out because sometimes you're like stuck on what you think is the easy answer and not seeing another alternative. All right, second one. P minus 9, P plus 5. No problem. Okay, then when we put numbers in front, things get a little bit more difficult. And there are methods that you can use to solve these, but I find that by grade 12, most students have forgotten those methods altogether. So because you've forgotten those methods, I could reteach you the grouping method or other shortcut techniques that you've forgotten. But you have the mental math skills within you to figure this out. Okay? And sometimes picking something that doesn't work is a great strategy to start. So I would say, if I was stuck on this one, knowing how factoring works and knowing how to check factoring, like if I factor this, and I'm going to try my best to get it wrong, so I'm going to have to, it's going to be hard a little bit. But if I'm factoring this and I multiply it out, in English, this is, from some of you are from French immersion, in English we have this like acronym that you might hear English students saying, oh, you just FOIL it. Have you ever heard an English student say that? No, I'm going to teach you the word FOIL. It's really simple. You multiply the first ones, you multiply the outside ones, you multiply the inside ones, and you multiply the last ones. And when English students are learning for the first time, they're like, learn the word FOIL to remember that they have to draw all the arrows. You probably just know to draw all the arrows. It's not really a big deal. But something interesting happens that in the FOIL part, the first ones always end up being your first term. The last ones always end up being the last one. And your outside and inside become like terms that need to be combined to the middle. And recognizing that pattern tells me, okay, if my first one's a 6a squared, I have options here. It could be 6a and 1, or 2a and 3a. Okay? And I can just put one down. I'm going to try to get this wrong. I'm going to put one down at random. Okay? I'm going to put one down at random. Oh, yeah, I'm going to really get this wrong. There we go. 6a and 1a. That makes 6a squared. That's a possibility. It could also be 2a and 3a. The last one is a 3. The only way to get 3 is 1 times 3. It could make a difference if I put the 3 here or the 3 here. Do you see why? If I put the 3 here, my outside becomes 18, and my inside becomes 1. And now I'm really proud because we are going to get this wrong. Right? If I need to get a positive 3, these either both have to be positive or both have to be negative. If I choose them both to be positive, can you see that the middle term now would be 19a? And it's going to be wrong. But by choosing one that's wrong, you will be able to then say, oh, I think I know what I need to do. I need 11. If I put a 3 here, that would make 9 on my outside, and a 2 here, that would make 2. And 9 and 2 seems to make 11. Now, personally, if I was going about this without any shortcut methods, without grouping, just going directly to the answer, this is how I would start. When I see 6, I realize there's 2 options, 6 and 1, 2 and 3. So I'm actually not going to put those numbers down first because I don't know which one it is. But when I see 3, because 3 is a prime number, I know that the only possibility is 1 and 3. And if I start with that, it really doesn't matter the order yet, because 1 and 3 technically is the same as writing 3 and 1 at this time. Now, when I go to write my first ones, and I need to get 6a squared, now I can start doing a little bit of mental math in my head. I can say, oh, 6 and 1, that's 18 and 1, that never makes 11. If I put 6 here and 1 here, that's 6 and 3, that doesn't make 11. So 6 and 1, if I thought of that first, I can eliminate it, that it doesn't work. If I then try 2 and 3, if I try the 2 here, the outside would be 6 and 3, that doesn't work. But if I try the 3 and the 2 here, I now see that this is 9a, that's 2a, and that would give me 11a. I can put plus and plus. Now, not to say that the methods, the grouping method or the different methods you've learned in previous years, they're not bad. But they take a long time to write out. They're very easy to make notation mistakes with. And they take a lot of space. And a lot of the questions we're going to be doing, we're going to be factoring all over the place. You don't have, room. You want to go directly to your answers. So we're going to try to get to these answers directly. For the second one, here, 2x squared, I would start with that. Because if it's factorable, that's the only option, right? But the last number, 35, has different options. 35 could be 35 and 1, or 7 and 5. Do a little bit of mental math here to see if there's any way that you can make 9. I put the 7 here, I have 14 and the 5 there. That could make 9 if I'm subtracting. I would need my 14 to be positive and my 5 to be negative to make a positive 9. And then I do a quick check. Do I still have the negative 35 that I wanted? Yes. So I would recommend at this point, you guys are getting better at your mental math. For factoring, try to do it directly. And if you're struggling with one, a great strategy is make your first ones work, make your last ones work, and get it wrong. Multiply it out. And as soon as you multiply it out and get it wrong, your brain will be very quickly going, oh, you should try this. I think this would work better. And you might get it wrong again. That's okay. But you'll find your factoring skills improve immensely. Difference of squares. What was this called in French? Something au carré.
Yeah.
Something au carré. What's the word? Difference. There we go. Now, the words in English and in French, they mean exactly what you see. The difference is because there is a subtraction sign. That's why it says it's difference. And both of these are squares. In other words, 25 is 5 times 5. It's 5 squared. 9x squared is 3x times 3x. It's 3x squared. And anytime you have a difference of squares, it will always factor to be 1 plus 1 minus. Now technically, that's a nice shortcut, but technically, difference of squares is exactly the same as regular factoring, because all this 9x squared, this is like 9x squared plus 0x is minus 25. And you're still multiplying things out, but now the outside and the inside cancel out, because one's positive, one's negative, you'll get 0. But instead of getting students to, hey, we should add a 0x and factor it like we normally factor, this shortcut is so nice and so easy to do that as soon as you recognize this is a perfect square and this is a perfect square, right, we can right away, well, it's got to be 7 and 7, and this has to be 9 and 9. P cubed and P cubed will give you P to the 6 when you multiply. 1 will be plus, 1 will be minus, and Q to the 4 and Q to the 4 will give you Q to the 8. And you can do very complicated differences of squares that would not be fun to do as regular factoring. As soon as you recognize perfect square here, perfect square there. So a lot of higher level math is requiring you to recognize things from the past and be able to work with them easily. And one of the things that I'm excited for you in this course is this course will make your algebra skills so much better. Like the algebra skills that you've been developing in grade 10, 11, and 12, you just get better and better and better at them. And then when you enter your university course in math, you're not making those same mistakes that you're making back in grade 9 and grade 10. And you're just, all of your numeracy skills just improve like crazy. Okay, so up till now, this should all have been stuff that, oh, and even this. Up till now, this is all stuff that you've done. And we're going to learn some fun new factoring stuff today as well. So first of all, sometimes you have more than one thing. Always look for a common factor first. Because if you start to factor this with 2 brackets right away, it's doable, but it's not easy because of that 3x squared. Right? But if you notice, hey, there's a 3 in common, I can take that out first. That's so much better. And then, of course, I put one, is it 6 and 1 or is it 2 and 3? It's a 6 and 1. This one too has a common factor. Notice I can pull a 2 and I can pull a P out. And then you look at the next one and say, does this fit any of my factoring? I see a difference. Is it a difference of squares? Yes. Did you ever have this question on a factoring quiz in grade 10 or grade 11? Because this one's interesting. It's interesting because it's a difference of squares, right? Because this is x squared times x squared. So on the test, you feel like, ooh, teacher was trying to trick me by putting an x before. I noticed, and I got x squared plus 1 minus 1. Yeah. And then you quit, and you go on to the next question and feel all proud of yourself. And what's happened? You missed that it made a new difference of squares in the second. The first one can't be factored anymore, but the second one could be. So if you want to have some fun, you could factor that. And it would be x to the 128 plus 1, x to the 128 minus 1. And the x to the 128 minus 1 could be split up again. And then you get 64, and then split up again, and get 32, and then split up again, and 16, and 8, and 4, and finally 2. And it would be super long in the end. No, don't do that. Okay. So sometimes we think we're done, and we should always take a look, right? You do the factoring step. You're going to take the time to multiply it out to double check, did I do the work above correct? And I think sometimes we as math teachers don't say that enough, right? Every time I'm doing math on the board, well, not every time, because there are times that I make mistakes. Sometimes I take shortcuts. And then all of a sudden they'll be like, what happened there? I'm like, oh yeah, I didn't check. But almost every time I do my work and then I check afterwards, does it match with what was before, right? But I do that in my head, and the students are watching and they don't hear that. But I should probably be saying it. Oh, I checked my work. But that would be kind of annoying, especially on the videos, because every step of it, I checked it. Not sure that would be so good. All right. If you had this and you were asked to factor, chances are you would be like, okay, this looks new. We have 1 plus 5x to the minus 1 plus 6x to the minus 2. This seems awkward. And that's because it is a little bit awkward. But what you could do, and what we start to notice, is some of the things that we used for factoring that we were limited to regular numbers before, we can just sort of expand those rules and say, what would it look like if I factored out an x to the minus 2? And you would say, well, there's not an x to the minus 2 in common in all of them. Or is there? We can kind of make it in common. In other words, if I take out, I just want to imagine it. If I take out an x to the minus 2, and I imagine distributing to 3 things, it's pretty easy to see in the last one I would just have 6, because I took out the x to the minus 2. But in the first one, I don't see an x to the minus 2, so it feels a little bit like, how could I factor that out? So instead I imagine, what would be here? So when I take x to the minus 2 and I multiply it by something, I get 1. And a little reminder that x to the minus 2 you could also think of as 1 over x squared. So now I could also think of this as 1 over x squared times something is equal to 1. What would that something be? Well, I would need that x squared to cancel out. So I would need an x squared on the top. Does it make sense that if you factored out x to the minus 2 out of 1, you'd be left with an x squared? And if I took out x to the minus 2 out of here, well, I would have x squared on the bottom. I want 1x left on the bottom. I would be left with 5x. And so what we did by factoring out that x to the minus 2 is we left us something that looks like what we used to factor. And then this one's a 3 and a 2. You'll notice that in my notes. If we're going to do basic factoring, I like to do the ones that make you have to think a little bit. Is it the 3 and the 2? Is it the 5 or 6 and the 1? Second one, you can see that there's a common factor of 3 in all of those. But I'm also going to want to take out that negative a half. The last one I think is the easiest. If you take out a 3 and that x to the negative a half, can you see that you're left with minus 15? Because the x to the negative half came out. But now, if you took out a negative half out of an x to the 3 halves, you would need, well, you can think of it, okay, this is getting multiplied. When I multiply powers with the same base, the rule is you have to add the exponents. So negative half plus, and I'm going to write it as 4 halves right now, would give me 3 halves. Does that make sense? But that then will just simplify to x squared. And if I add half to this one, it's going to equal to an x. So if we take out the 3x to the negative a half, then we're left with x squared minus 2x minus 15, which factors nicely. To this. Oh, very good. That's kind of exciting. Oh, you can, like, right? You can factor other fun things, right? This isn't a difference of squares, right? Unless you bend the rules, which is perfectly fine. Right? Where so long we just did regular numbers, but why shouldn't it work with all numbers? And it does. So you can factor this as a difference of squares, even though you have a 5. But 5 is just square root of 5 times square root of 5, so why not have it work? And now you can actually solve these questions that look very complicated. What could I do? I could take out the 3 and the x to the negative 1/3. And things turn out nicely. This factors even further now. Let's see if this works. I should erase it behind there. We have no idea what the answer is. Now, factoring changes it to being multiplied. And now we're multiplying ones here, 3 things to equal 0. And one of them has to be 0. I'm hoping you can see this one, right? And this one. But I want you to think about the first one. You can use whatever you want. So another thing is the rules that we have in the past, we got to know how to work with them. Here we've got an exponent that's a fraction and an exponent that's a negative. So we need to think a little bit about this, because this is really what we're asking. When is this equal to 0? Okay? If you're not really wanting to do a lot of work, your brain would probably say, let's just go with 0. Yeah, you know what? I think we should go with 0. It must be right. Let's not think about this. Let's put 0 and keep going, right? 0 is not the right answer, right? But some of you are like, that was probably, I was hopeful that that would be your first inkling. You'd look at that and say, I think it's probably 0. But it's not 0. Why? Because this is technically a negative exponent, moves that to the bottom. So that's the same as that. This technically means the same thing as a cube root. Nope, that's not an x anymore. Right? An x to the 1/3 is a cube root, just like an x to the 1/2 is a square root. And now we're trying to solve, when is this equal to 0? And the problem is, it's never equal to 0. Because the only time, like this is a fraction. Technically, what I could do next is I can multiply both sides to get rid of the fraction. And I get this wonderful statement. When is 3 equal to 0? It's not. If you think it is, give me $3, I'll give you none back, and we'll be all good. That's when 3 is equal to 0. Usually it doesn't end well. Someone's mad at the end of that. There's no solution to this. So these are technically our only 2 answers. But I wanted you to look at that because I think you'd be tempted. Because you see an x out front, you think, oh, it could be 0. But that x, if x is 0, that x would be on the bottom as a 0, and you're not allowed to divide by 0. With limits, we get to play around with dividing by close to 0. Right? It's like calculus, you get to play, like things in math you're not allowed to do. You're like, ooh, let's play around with, it's human nature. Not allowed to do that? Well, let's see what happens if we get close to doing that. Play around with that a little bit. Okay. So, bell's going to ring shortly. We will leave factoring from the remainder theorem and synthetic division from grade 12 review for next class.